இல்லையே சார், திரும்ப வெப்சைட்டில் போய் பாருங்க. நம்பர் 9880. ஓ சரி.
Uh, Good afternoon to all the participants. Actually, our esteemed chief guest is getting a little bit late to join. He's requesting 5 minutes. He will join it. Sorry for the inconvenience to all the participants. Actually, speaker is joining in a 5 minutes. All be patient to wait for 5 minutes. We'll start in 5 minutes. Sorry for the inconvenience again.
Hello, good afternoon.
Sir, good afternoon, sir. Sir, am I audible, sir?
Yes, sir. Yes, sir. You're audible.
Yes, sir. Yes, sir. Sir, 2 minutes, sir. Will start.
Yeah, sure.
Good afternoon, everyone. I am audible. Good afternoon, everyone. Myself, Dr. Vijay Kumar Nadesan. I am working as the assistant professor in the Department of Civil Engineering. I welcome to all the participants and also today session, afternoon session, chief guest for attend this second session of FDP AAC 2025. Once again, I will thank to the chief guest to accepting this, accepting our invitations to give the speech about the application of geometrics and SWOT plus for hydrological modeling, a special focus on urban centers. So I will speech about the today's chief guest. The Dr. Chandan MC is currently serving as a faculty member at NIT Surathkal. His specialization is in geoinformatics and hydrological modeling. The chief guest has strong experts in remote sensing GIS, urban growing modeling, and spatial decision support system. So his research work has published in numerous reputed journals and international conferences, and also he published several book chapters, which is reflecting his deep commitment to advanced knowledge in his field. And also he participated 30 plus conference and also presented. uh, in addition, he invited give the many talk about his research work in the various institutions. Dr. Sanjan also inspired the student and the professional like through his engaging the lectures and his on workshops. The exports is in SWOT plus modeling has enabled more accurate simulation of watershed behavior, helping planners and engineers make data-driven decision for suitable development. Today, he will talk us through the application of geoinformatics and SWOT plus in hydrologic modeling, and also he highlighting the how spatial tools and simulations framework can enhance on watershed management and also flood predictions. Finally, he will concluded sustainable planning for future development. Once again, I thank you, sir, for accepting our invitations. Now hand over to the our today's chief guest, Dr. Chandan MC. Sir. Thank you, sir.
Yes, sir. Thank you. Thank you so much for that wonderful introduction.
Yes, sir. One more thing I'm missing.
Yes.
Yeah, sir. You are the reviewer in various journals, reputed journals. I've seen in your profile, sir. I'm missing that one. Thank you, sir.
Thank you. Thank you for that. Is my screen visible?
Yes, sir. It's visible, sir.
Okay. So I would like to thank all the organizers of this FDP for inviting me over this FDP for the talk. Today we are going to discuss about applications of geoinformatics and SWOT plus for hydrological modeling. The thing is, I want to just introduce you all for the next 1 especially why I am showing this is because this part I've kept it as a hands-on, wherein I can demonstrate for one small portion of the Bangalore region. So let us start this session. So these are some of the key concepts that are covered in this particular lecture. So we'll start with basic hydrological process, water balance equations, and SWOT model and how SWOT model behaves, its features, and various different kinds of approaches that are available for simulation of hydrological processes. SWOT model, the input, what is required for this SWOT model, and finally, what output you can expect from the SWOT model. So these are the things discussed, and further we'll also see urban Yeah, very sorry for that interruption. Now, can you see the screen?
Yes, sir. Yes, sir. It's
Okay,
visible.
okay. Thanks. So in the second part, we will be looking mostly at the urban flood modeling for Bangalore city. So with this, let us try to understand the hydrological process. As you are aware, uh, the hydrological cycle, basically we are dealing with the water cycle, with how the water moves from one location to another location. That is the gist of our hydrological process in various different forms, whether it is in the form of a liquid or a solid or a gaseous state. On the earth surface, we are more concerned upon the earth surface rather than oceans and atmosphere, because we are directly depending on the water that is on the surface of the earth. So if you look at the hydrological process, there are certain important aspects such as evaporation and transpiration, evapotranspiration, condensation, dew points, precipitation, and runoff. These are some of the important aspects. Now, on to the right, you can see the water cycle. So can you just tell me how many of you believe that this is the correct representation of water cycle? Because most of us have been studying water cycle since our engineering days. So how many of you can confirm, at least one or two, if you can say yes sir, this is what we have studied in our during our study period. So can you, one of you or any one of you can confirm the water cycle what we are trying to see here?
Yes, sir. It's understood.
Yes, yes. So as you all agree, this is what the conventional water cycle used to look. But now if you see the image, this is the recent, very recent one that has been given by United States Geological Survey. So this is the latest addition for the hydrological or water cycle. So you may ask, what is the difference between the previous and this image? Of course, here if you see, there are a lot of other things that have been added. And they have also taken into consideration the impacts of climate change. For example, if you see there is urban runoff. Yes. Yeah. For example, if you see there is urban runoff, and if you see here, we have the industrial wastewater use, grazing water use,
What has been,
and
sir?
sorry.
Raise the hand.
Yes. Is there any questions? Can I go ahead?
Yes, sir, you can go ahead.
Yeah. So you can see many of the aspects that has been taken into account, and which is also giving you a proper picture of water cycle with respect to the climate change. So in future, if you are trying to communicate with any of the journals, maybe this particular image might help you for briefing out with respect to the latest hydrological process and its flowchart. So as you all know, the watershed, that is the spatial unit of hydrology, what we consider for all our analysis. So this is how the watershed looks like. It is having a proper boundary, and in within that boundary, you are having kinds of streams. That is the first order stream, second order stream, and higher order streams, which is then called as rivers and river system itself. So by definition, if you see, it is an area of land in which all of the incoming precipitation drains out to one particular place. Mainly that is due to the topography, or we can call it as the elevation and depression. So when we look at the watershed using the water balance equation, we have three important components. One is called as the precipitation. The second one is called as the runoff. and the third one is called as evapotranspiration. The precipitation is mainly the atmospheric exchange between the Earth's surface. And here we can see the precipitation in terms of rainfall, in terms of snowfall, or many other types. When you refer to the runoff, we have the surface runoff, that is over the surface, lateral flow, and the groundwater flow. So these things are accounted for the runoff. And when we look at the evapotranspiration, this is mainly with respect to the plants, the evaporation and transpiration happening from the plants, and evaporation happening from the open water body like rivers, ponds, etc. And also we have the evaporation that are happening from soil surface. On the other side, if you see, we have the storage. So once we have the precipitation, and you cannot say that whatever amount of precipitation we are getting, we are completely using everything. No, that is not possible, because we have to account for runoff and evapotranspiration. Then you have the storage change, that is in terms of soil moisture, in terms of plant interception, groundwater, and water body itself. So here we are trying to do is we are trying to measure the flux or the is happening in the hydrological cycle in terms of so many millimeters per day. For example, if you take the evapotranspiration, we are measuring it in terms of millimeter per day. So time span is very important when you're trying to model the hydrological process itself. So it can be sub-daily, it can be daily, or it can be monthly, or it can be annual. Now, if you see the figure on to the right, this shows the hydrological model components. This is very, very important when you are trying to do a model. And here we are referring to a system boundary. That means boundary conditions is very, very important. And how do we define boundary conditions? Any idea? Can anybody give me one example where we define the boundary conditions for a hydrological system? Let this session be interactive, otherwise it will be very monotonous for you. So any answer? What do you mean by boundary condition? Anyway, this I will show it in the hands-on also. Okay, let me put it this way. So basically, in majority of our hydrological process, when we are dealing with the boundary conditions, we are giving the upstream and downstream boundaries as certain values to be considered. But as a whole, if you are taking into consideration the entire area of study, that can be defined by the system boundary conditions, and over which we are expecting some kind of precipitation that is happening, and we are trying to quantify that. So ultimately, once the precipitation, we are taking it as input, and that precipitation is what is falling on the surface, that will be collected at one particular point, which is called as the stream flow measuring station. So here, most important thing is one is input variable, which is nothing but the precipitation in our case, hydrological system that is defined by the boundary, and the output variable, which is defined by stream flow. Then if you see the hydrological modeling, we have the model category by spatial delineation. We have the lumped model, wherein we consider all the sub-constituents as one lump. So that is why it's called as a lumped model. Here you can see the spatial variability is disregarded. The entire catchment is taken as one particular unit. So that is why we're calling it a bulk or a lumped model. Okay, then we have the second one, which is called a semi-distributed model. So here we are considering series of lumped models, small lumped models put together. So that becomes semi-distributed model. And then the third one, which is called a spatial distributed model by grid cells. So here what we are doing is the entire catchment area, whatever we are considering, we are distributing in the form of small grids. So here we are accounting directly for spatial variability. So that is very, very important. And if we talk about the strengths of these models, if you see the distributed model, this is directly related with the physical model what we have on the Earth's surface. So you can directly relate to that. All the hydrological processes undergo this distributed kind of a system, so that you can estimate the more accurate data in this. And majority of the models like MITS and Velma, all of this used this distributed kind of hydrological modeling. And trying to describe the hydrological processes by scale, if you see, you can also describe with respect to scale. we can call it as a micro scale if you are trying to deal with the local, uh, region. Then if you are trying to deal with a hill or a small catchment or multiple catchments, then you can say it as a mesoscale, then macro scale for large catchments, and so on. So this is how we define with respect to spatial scale. And another one is the time scale. So many of the hydrological events can be put up in terms of time. So that is why we are having minute wise, hour wise, day wise, month wise, and so on. Okay. Next, if we speak about hydrological models and modeling systems, so we have certain tools which are developed exclusively to visualize and understand and further simulate the hydrological processes. So, for example, we have the one which is called as SWAT, which stands for Soil and Water Assessment Tool. And this is a small watershed to river basin scale you can apply. It is not restricting only for smaller watershed. You can even apply on the river basin scale. So basically, it was developed in US Department of Agriculture under the Agriculture Research Service. So now, if you can download, this is open source software, that is the SWAT plus model. So you can freely download from the website that has been given here. And if you try to look at the application of SWAT model, so basically here what we do is we try to predict the impact of land management practice on water. So water is our primary concern. On sediment also you can here you can also analyze the how much sediment is carried by a river. Sediment analysis. Agriculture chemical yield can be estimated in complex watershed. And also you can have information about land use and management conditions over a long period of time. So basically, if you look at this SWAT model, why is it so unique is because here we are considering not only with respect to the entire watershed, we are also considering subbasins and we are also considering the HRU. Now, what is HRU? HRU means it is hydrological response units. So here you can see HRU is comprised of soil layer, crop layer, slope layer, and other. So once we see this as a HRU, we also need inputs in the form of weather and soil data, land use, and digital elevation model. So ultimately, what we would be able to model is with respect to the flow of water. So here you can see then sediment and sediment yield, and then you can also model for nutrients. So as far as this lecture is concerned, we are not worried about sediment or nutrient. We are worried only about water. That is nothing but the hydrological flow modeling. Then if you see the 8 important components of SWAT model, we have climate and hydrology. Nutrient and pesticides is optional if you are trying to work with nutrients, agriculture, chemical yields, etc. Soil erosion, land use, management practices. So management practices again is optional because this comes under irrigation techniques, what kind of different irrigation techniques you are using. And then we have the channel processes. So here mainly we are concerned about the open channel flows and water bodies. Okay, and then if you look at the SWAT, it provides a more flexible, spatial representation. So you can have many layers which can provide you much information about that particular area. So if you see the basic specifications of SWAT model, so it is designed to predict the impact of land use and management practices on water and sediment. So what you can understand from this is basically, spatially, if you consider it is a kind of, you can either treat that as a lumped model. As I said, the entire catchment, you are treating it as one, or you can treat it as a semi-distributed model, or you can treat it as a distributed model. So if you take the advantage, you can treat your watershed in all of these 3 different spatial scales. So that is the one of the most important advantage what we are having in SWAT model. Otherwise, if you try to consider with respect to the temporal aspect, that is with respect to time, you can either perform a daily analysis or you can also perform an hourly analysis. Of course, without saying, you can also perform based on monthly or annual analysis is also possible. So it is a continuous time model that operates on daily time step. That is the least time step what we are talking about. Hourly and minute wise time step is not available. And if you see, it is computationally very, very efficient, and it is also capable of continuous simulation over a long period of time. So apart from that, the necessary information what we should seek from this model before trying to do the modeling is that the infiltration and water flow, whether it is allowing the SCS curve number, soil conservation service curve number, and all other characteristics such as surface runoff, whether it is macropore or evapotranspiration, is it allowed to model these things in the SWAT itself. So once we understand that, next we are moving ahead with model features and approaches. So here basically what we are trying to do is the physically based models. So that is specific information we are trying to give for a catchment. And physically based model means however it is happening on the ground, on the surface of the earth, we are trying to replicate the same thing on our models in our computers. So that is called as physically based model. So this is mainly suitable for large catchment basins, and even you can go up to continent level. Whereas if you try to consider the second part, which is called as semi-distributed, so here we are much worried about the HRU, that is hydrological response unit, because we are not considering that bigger area like a large catchment for an entire river. For example, if you take Kaveri basin or Krishna river basin, basically you are talking about Maharashtra, you're talking about Karnataka, you're talking about Telangana and some part of Andhra Pradesh also. So we are not considering that big area. Then you can go for semi-distributed, wherein HRUs can be generated, that is hydrological response unit. That is nothing but simple overlay of the land use, soil, and slope in terms of distal elevation model. You can derive the slope, etc. And this is not a lumped model, and neither it is a fully distributed model, but it is a mediate model. And then if you look at the long-term impacts, so how you can collect the data, and you can try to kind of see the effect for near effects, that is around 5 years, or long-term effects maybe like 30 years or 40 years or 50 years also. And then if you see, the temporal scale can vary from daily to monthly to annually. Just now we were discussing in the previous slide. And also we have certain readily available data sets. So what are the approaches to simulate the hydrological process? So this is one of the most important point. So here, first we should try to understand the water balance and then surface runoff. So what is the connection between the water balance, surface runoff, and other parts in hydrology? What we call it as the infiltration, the evapotranspiration, the soil water, groundwater, and channel process. So all of these things, what we'll do is for the next couple of slides, I'll just brief you about these things. Many of you are already aware of this. Just it will be kind of a highlight for you. So in the water balance, what we are doing is we are trying to estimate the soil water content with respect to the initial soil water content what is available, considering remaining all the hydrological parameters. Like for example, you have the precipitation, you have surface runoff, then you have evapotranspiration, seepage flow basically under the soil, and then you also have groundwater flow that is available. So all of these, how it is contributing to estimate the soil water content, that is our main concern. That is water balance only for soil point of view. Here we are speaking with respect to surface. Then second one is the surface runoff. So here, as you can see, this is guided completely with respect to SCS curve number, that is soil conservation service curve number. So what is curve number? Basically, it is it does not have any units, and the curve number can range from 0 to 100. How do you define curve number? Basically, it is defined with respect to the absorption capacity of any material. So here we talk mostly about the soil. If you are referring to soil, about its permeability and various kinds of land use and how the water retention is there in that particular land use. So basically it is a empirical equation, and it does not have any derivation or proofs. However, it does not have even the units also. This is just a number. So now the curve number can vary as small as 0, and it can go up to 100 also. So that depends on what kind of feature we are looking at. Then in this particular table, you can see the curve numbers that are being provided for various types of land cover. If you see open spaces, basically the curve number is very less. It is around 39, 61, etc. under various soil groups. And if you see impervious area, this is very important. Why it is very important? Because today all our the objective of this entire session is to speak about urban floods. We are speaking mostly about impervious areas. So that is where, if you look at the values of impervious area, that is mostly above 80. And if you look at the commercial and business areas, industrial areas, everything is we are trying to consider mostly the curve number as more than 80. Then if you try to understand the infiltration rate, so here we need to first quantify what is the soil profile, whether it is homogeneous or not, and then how is the soil moisture distributed in that soil profile, and whether the soil, the wetting front is completely saturated, partially saturated, or is there a scope for saturation. So that needs to be understood. And with respect to that, something what is important when you are trying to refer the infiltration rate is that we have to understand what are the hydraulic conductivity properties of the particular soil. For a saturated soil, it will be different. For an unsaturated soil, it will be different. So here we are trying to just understand with respect to the type of soil, its bulk density and porosity, and whether the composition, how is it made, the clay content, sand content, and we can also go with various textures. The next important aspect is evapotranspiration. So this word, as you can see, it is a combination of both evaporation as well as transpiration. So there are two kinds. One is the potential evapotranspiration, which can be estimated by Penman-Monteith equation and Hargreaves equation. So when we look at the actual evapotranspiration, so here basically we are talking about the canopy interception and the soil also. So if you see in this figure to the right, so basically here we are dealing with the you are dealing with the potential evapotranspiration and what are its the various components. So here we have the equation that is given by Penman-Monteith. So that is of course that is given by FAO. Here you can see the evapotranspiration is guided by various factors. Okay, so one among the most important factor is net radiation. So the net radiation that is available at that particular point of time. Then you have the soil heat flux. Okay, and here one important thing is you should also take into consideration the air temperature. So the air temperature is generally measured at 2-meter height, and wind speed is generally measured at 2 meters height. This also need to be taken into consideration. And apart from that, we also have saturation vapor pressure. So all of these will be contributing to your evapotranspiration. So that is given by FAO Penman-Monteith equation. Then if you look at the soil water interaction, so here majorly the soil water is uptaken by the plants, and also we have the saturation condition, field capacity, wilting point. Can anybody tell me what is the wilting point for a plant? Any answers? Let us be interactive so that everybody will feel connected. Can anybody give me what is wilting point? Any answers? If you are putting it on the screen, I'm unable to see the screen. Okay, fine. So, and then we also have plant water capacity. That is, we call it as available water capacity for a particular plant. So saturation conditions means all the pores and all the voids will be completely full with water. Field capacity means just the available water that is required for the plant growth that is being fed. And wilting point means there will be no water at all, okay, for the plants to grow. And then there is another term which is called as permanent wilting point. If a plant reaches permanent wilting point, then it is very difficult for us to bring back the plant to its lively state. So these are some of the basics of soil water interaction. Then we have another, that is nothing but the groundwater interaction. So in the groundwater, basically we are trying to consider the groundwater recharge, the groundwater flow, and we are trying to estimate how the groundwater behaves with respect to if you have a confined aquifer, if you have an unconfined aquifer, how it is going to behave. These properties are going to be considered. Next, we have the channel process. So here, basically, we are trying to see the open channel flow. And main assumption, what we do here is we assume the channel to be trapezoid in shape and the side slopes of the trapezoid to be assumed as 0.5. Now, when we look at the steady state, of course, all the channels are considered and assumed to be steady state flow rate and velocity when we consider. So when we want to try to estimate the hydrological process, especially with respect to the runoff. So here we are basically talking about steady state runoff, and this is guided by Manning's equation. This is very, very important. What is Manning's equation and how it can be varying from one place to another place. So that also we'll see when we try to model using the ECRA system. And what decides this is the water depth, the width of the channel, and the length of the channel. So this is how it will be related. And if you try to understand the flow storage routing, so here we are basically considering the two parts, as you can see in this figure. One is the prism storage, and that is in the bottommost portion. And then you have the wedge storage area, that is in the top storage area. So how do we achieve the balance? The balance is with respect to the transmission loss, the evaporation, the diversion, and the bank storage. Okay. So with these basics, now we'll try to understand various different models. The first one among that is the SWOT model, as we discussed in the initial 2 to 3 slides. So SWOT model, basically here, if you see the main important aspects, we need the daily rainfall data. We need the maximum and minimum air temperature. We need wind speed, solar radiation, humidity, land use, soil, and topography. So these are the inputs that are required for SWOT model. So once you have all these inputs that are ready for your area of analysis, then you can calibrate the model and run the SWOT model to obtain the runoff, the soil erosion, or even water quality for HRU, that is hydrological response unit. That is nothing but the small areas. It can be on a daily basis, it can be on a monthly basis, or it can be on a yearly basis. Suppose if you are working on a monthly basis, then you can estimate it for subwatershed. That is a little bit hierarchy if you take. So that is a much bigger than HRU, that is called as a subwatershed. And if you are trying to analyze for yearly basis, then you can model it for a reach segment or a bigger stream itself. So now the hydrological response unit, this is mainly due to the land use, different type of soil, different type of the watershed, what we are referring to. So we define with respect to land use, soil, and DEM. So that is called as hydrological response unit. And also, if you see this is the HRUs. Basically, they're used for the simulating of hydrological cycle, including the weather parameters. Here we are also considering the evapotranspiration, infiltration, percolation, as well as surface runoff. So if you want to see what kind of input and output is required, so input data, we need DEM. Can anybody tell me where we can get the DEM from, digital elevation model? You can unmute yourself and you can speak, or if you are not able to do that, you can even give the response in the chat box also. Okay. Fine. So basically DEM, we are trying to obtain a 30-meter DEM from, the SRTM. And then we have the land use. Land use can be taken, considering the Landsat data that is of 30-meter resolution, or you can even consider Sentinel, which is of 10-meter resolution. And then we have the soil layer. Soil layer can be derived. Then location of meteorological station. So this can also have attribute data along with the location, that is X and Y coordinates. You can also have additional readings such as humidity, temperature, wind, etc. And then if you see the GIS processing, so we have the first and foremost method, which is the watershed delineation. As soon as you feed in the dam, the first thing what happens is you need to delineate the watershed. You need to give the boundaries. And once the watershed is done, then we identify the subbasins within that watershed. And within that sub-basin, we'll try to understand what are the different kinds of streams that are available. So the streams, what we are referring to here, that can be the primary stream, secondary stream, or tertiary, or any other higher order streams. And then also we have to generate the hydrological response units. So the hydrological response unit is one among the last processes in the GIS environment. Then when we look at the configuring input files, so this is mainly with respect to your configuration with respect to the SWAT input in various domains, and you can use certain configuring table to make ready the input. Then we have the model run. So here basically we are conducting a sensitivity analysis, and most important is model calibration. So once you calibrate the model, then you can assess its how good it is. That is nothing but the model validation. And finally, you can obtain the results in terms of reports as well as the parameters that can be very optimal. So now these slides will summarize the entire model setup for SWAT as we discussed. So we need HRU consisting of landscape, that is the land use, soil and slope classes for the to mimic the real scenario on ground. So slope will take care of the topography, soil will take care of the curve number and infiltration capacity, soil water interaction, etc. Land use will give you again in terms of curve number, whether if it is urban areas, what should be the curve number, whether if it is semi-urban, and so on. And then you have the apart from these data sets, you also have the climate data and weather data that can help you in simulated flow. So what you can do is once you have all these data sets, you can simulate the flow for your region for a particular year, let us say 2024. And 2024, you already have the observed flow. That is how you will try to compare the simulated flow versus observed flow, and you will try to estimate what is the accuracy that I'm getting. So once you have the satisfactory accuracy, then you can go ahead and predict the flow conditions. So this is the general setup of SWAT model. Then if you want to run the SWAT model anyway, since due to time constraint, I'm not going to give the demonstration of SWAT model, but I'm going to give you the demonstration of HECRAS. So just for time being, we'll try to understand how to run the SWAT model. So it starts from creation of a project, watershed delineation, as I mentioned, then the input with respect to the HRU, that is nothing but the land use, soil and slope data, then HRU distribution. And then if these things, the rainfall, temperature and weather data, these are additional data sets what you are trying to give apart from the basic data sets. Now what happens is when you can even run the SWAT model without giving the rainfall input, temperature input and weather data input, just by having the land use, by having the soil layer, by having the DEM or slope, you can directly run the model. It will definitely give you what kind of flow is to be expected. But when you try to include the rainfall data, temperature data, humidity data, and etc., so that will help your model to be more realistic. So that will give you more accuracy in terms of real-time data. And then we write the SWAT input files, we run and we check. So that is coming under SWAT checker. So ultimately we will be having the SWAT output for flow conditions. Now we'll move to the second part of this lecture. Here we are focusing mainly on urban floods. So today's topic, as we are speaking about the urban flood modeling, and how we can use HECRAS or HMS, and how we can perform it on majority of the urban areas. So here you can see this image. This is depicting the Bangalore region. This is the BBMP boundary. And Bangalore region, if you see, we have three different valleys. The first one is called as to the north, it is called as the Hebbal Valley. And to the southwest, we have the Rishabhavati Valley. Today, I'm going to show you one demonstration on Rishabhavati River. And actually, it is a river, but it is very unfortunate that the river inside the city is now converted into a big drainage. That is, sewage. They have converted into a sewage flow. Then we have the other valley, which is called as Koramangala and Charlaghatta Valley. Anyway, we are not going to focus on this. We are going to focus only on Rishabhavati Valley. So let us try to understand some causes for urban flooding. So first and foremost important is there is no water infiltration happening in our urban areas. And these images are the very recent flood that has happened during May and June in Bangalore. So as you see in the majority of the urban areas, we have very less scope for water to infiltrate into the ground surface. So that is mainly either due to the roads that are being constructed or due to the buildings that are being constructed. That is point number one. Point number two, we have enough, threats like encroachment of lakes, encroachment of water bodies, encroachment of wetlands. So if you see the drainage, so there is a lack of proper drainage system. So earlier, if you see the Bangalore, so it was all well connected. The drainage system was proper. That means one lake in the upstream, if it is full, then that is following a natural drainage or the natural topography, and the water, excess water is going to the next lake and so on. And if you see even the series of streams that are being generated from the Bangalore city, as Bangalore, it is in the it is kind of a cliff, and these streams finally they are going and meeting Kaveri, River Kaveri in Tamil Nadu. And then we have, apart from this unplanned development, infrastructure failure, etc. Apart from this, we have certain natural causes also, that is heavy precipitation and flash flood. So basically, these are attributed to climate change and slow snow melt in southern part of India. This is not a problem. River floods and overbank flow and coastal floods. Now, if you see how we can make use of the satellites for monitoring the urban flooding, we have the satellites from ESA, European Space Agency. We have Sentinel-1A and 1B. We can also perform a very good hydrological model, that is in terms of urban flood simulation, using SAR data. Please keep this in mind. So that SAR data can be taken from Sentinel. So this can be one separate session. We can also have one separate session wherein we can see how to simulate the urban flood using SAR data. Then if you come to the other side, we have the Landsat, which is a optical data range. If you see Landsat starting from 1972 up to presently we are having Landsat 9. Then we have the TRMM. Earlier, we used to have this mission TRMM, but it was stopped in 2015. Now the replacement for TRMM is global precipitation measurement. After 2014, we are getting the continuous data from GPM. Then we have MODIS Terra and Aqua, and also we have other satellites like SMAP, soil moisture, active, passive, and etc. SRTM is basically we are deriving the DEM, digital elevation model, from SRTM. Then if you look at the various satellites that are available for urban monitoring. So apart from whatever I mentioned, you also have the characteristics like spectral measurements, and also parameter measurement like precipitation can be measured directly from TRMM and GPM, and soil moisture can be retrieved, and so on. So for today's hands-on session, what data? Basically, I'm going to consider the data that is available, that is in the form of terrain, or you can call it as digital elevation model. That is from SRTM. That is, we are going to consider the digital elevation model, and therefore the slope can be generated. Now let us go to the hands-on part. I would like to start the hands-on part. So for this hands-on, I'm trying to use HECRAS version 6.6. So this is how it looks. Can anybody confirm whether you can see the screen? Can we go ahead? Okay. So to start with, what I'll do is this is the home screen of HECRAS. So ultimately, we are going to simulate the urban flooding. So here in this particular session, we are going to see for urban flooding for Bangalore. So first I'll go to file, I'll say new project, and I'll create one folder wherever I need. For example, here I'm going to one particular folder, expert talk, and here I'm making one folder which is called as BLR underscore flood. Okay, that is the name I'm giving. So under this, the title would be flood modeling or flood one. You can give it as per your convenience and then say OK. So now it is asking whether you want to start a new project. So I can say yes. So now I have created a new project. And once you have created the new project, then what you're going to do is you are going to see this at the bottom right, US customary units. So this you need to change because we are dealing with SI unit. You can go to options and you can say unit system. So here instead of US customary unit, you can select the SI system and say OK. Say yes. So now you can see bottom right, it has been mentioned as SI units. Okay, this is the first step. Then what we'll do is we'll try to go to GIS tools and then RAS mapper. So this will open you a new window. And here, first and foremost is we have to go to project and say set projection. Why we need to set projection is because the system has to understand where you are trying to work. Okay. Yes. So I'll go to project and set projection. So here I'll go to, you can go to the file where you have saved the data. So here I'm considering this Bangalore region, the rectangular boundary for Bangalore region. I'll try to open this. So here you can see the properties, WGS 84, UTM zone number 43, and the corresponding spheroid. And here you can see the X and Y, that is in terms of UTM coordinates. All the values you can check. So once you have checked this coordinate reference system, then you can say apply and say OK. So now it is set. I would just like to show you the files what we are dealing today. I'm opening QGIS to show the layers. Add layer, raster layer, and here if you see, I have one raster which is called as DEM. So this is the DEM, and if you want to see to which portion it is belonging, you can turn on the satellite maps. You can turn on the satellite image. Both of them you can try to open it, and this. So here you can see we are having, you know, so this is the one. So here we are having the DEM. If you want to see the location better, you can just turn off this. Can you see this? So this is the DEM what we are considering for Bangalore region. Okay. And if you see satellite image, yeah, this makes sense. Now you can try to zoom in here and you can try to see this is the DEM, and yeah, this is the urban setting. This is how it looks. If you try to overlay DEM on this. Okay. So this is just a brief introduction about the dataset what we are going to consider today. Now we have already set the projection. In the next step, what we are going to do is we are going to select the DEM. So I am going to project again and create a new RAS terrain. So here you can say add, and you can navigate to the data set where you have the DEM. You can select raster data DEM and say open. So now you can say create. So once you can see the terrain is complete, you can say close. So here you can see this is the DEM what we were speaking about in the QGIS. Okay. So now we have gotten the DEM. So let us try to add another layer, that is nothing but the map layer. So here I'll say add web imagery, just like we saw in the QGIS. You can also call in the Google satellite image here and then say OK. If you want to try to visualize, and select the layer on, and once the layer is on, you can set the transparency. You can change the opacity to maybe 12%. Okay. Yeah. So this is how it looks. You can see if you try to zoom in into a particular area. Now, since I've set the transparency, you can see the variation. So now let me try to a little bit, to try to improve this a little bit. So yeah, now you can see the DEM is kind of blended with your Google satellite image. Okay, fine. So next, what we do is we try to set the geometry. Okay, as of now, you can just save this, and now we can go to geometry. And in the geometry, what we are going to do is here we can directly go to geometries, select the geometry, and then create new geometry. So here you can give a name. So I'm going to give river for this and then say OK. So you have created one new RAS geometry and then say close. Fine. So once the geometry is done, then you can go for editing the geometry. You can click on this river and say start editing, just like any of the GIS tool. Then the first one is you need to go for the center line digitization. You are going to click on reverse. And once you click on reverse, it will be available for digitization. Okay. So now what I'll do is, let us try to digitize with respect to Google image. Just give me a second. Okay, so here we can find one of the areas where there is a natural, drainage layer. Please let me know if you can see the screen completely. Yeah, so can you see this now? There is a kind of drainage layer. So what we are going to do is we are going to simulate the flood if at all there is an urban flood in this region, because here you can see it is a balance. You have the green portion wherein you have the vegetation, and also you have core urban area, and you have this drainage which is passing by. Drainage means it is a stormwater drainage, of course. So let us try to delineate this. So here what I'm doing is I'm trying to first trace this in the form of river. Okay. So whatever distance you want, you can just double click. So now our river stretch has been delineated. Now what you can say is press OK. This is done. So this is how it looks. So after every addition of, let us say now the river has been done, you can say stop editing so that you can save this. Okay. So this is the main drain that we have delineated. Fine. So next what we are going to do is we are going to draw bank lines. So what do you mean by bank line? Bank line is nothing but for any river, if you consider there is a left bank and a right bank. But unfortunately, in this particular image, if you see this entire stormwater drain is occupied by, I would say this is encroached, not even occupied. This is encroached. So let me take some distance, maybe some 5 meters from the main canal. So this is how you delineate the bank. Just give me 1 minute. Starting this bank line from here. Let me not go to the micro level, otherwise zooming in and zooming out will be difficult. Just you can assume some 5 meters, 10 meters, depending upon your study area. Yeah, so I've created one side of the bank. Now I'll try to create another side of the bank. Maybe again, you can take 5 meter or 10 meter accordingly. Okay, so now it has been created. Next, what you do is, so once the bank lines are created, next we'll be able to do the flow path. So here again, I'll say save. So the bank lines are saved. I'll create the flow paths, edit geometry. And maybe from here again, you can take some buffer and start creating the flow path. Then you have one more flow path on the other side of the river. Okay, so now you are saving this. Okay, so your flow path is done. Now what I do is I'll go to reverse, edit geometry. I'll try to add cross sections. So you can draw as many as cross sections you want. So for now, I'm just taking a minimum of some 6 or 7 cross sections. Okay. And again, you have to save this cross section. So once that is done, then you can go to file and save. And you can close this for now. Now let us go to edit and say geometry data. So in the geometric data, you can go to open geometric data. So this is the river, whatever we created. Now you can see whatever we had digitized, the stretch along with the upstream and downstream, you can see the flow direction as well. Okay. And if you want to see the cross section, you can click on this. So you can just move around and see each cross section, how it looks with respect to elevation, and also you have the station names. Okay. And then next is you need to go to tables. So here you can pick up the Manning's coefficient. So as of now, what I'll do is I'll set all the values to 0.035. But what you can do is I'll share one table, the link to Manning's coefficient. Depending upon your area of interest, what kind of urban area is present, how much percentage of urban area is there. Depending upon all those things, you can set this Manning's coefficient. So once this is done, this is basically Chow's Manning's coefficient you can refer to, or the link I can share it with you also, no problem. And then you can say OK, and then you can say save geometry data, and you can close this. So now you can see we have also saved the geometry as a river. Then next you can go to edit, and here you have the study flow data. So under the study flow data, you can go to add profiles. So here I'm just going with a trial. I'll add 3 profiles. Okay. Once you add 3 profiles, then you can go to the options and say edit profile names. The profile number 1, you can call it as 2-year return period, and profile number 2, you can call it as 10 years return period. Profile number 3, you can say maybe 30 or 50-year return period. Then in this, you can insert the values. For 2-year return period, I'm having maybe some 700. And for 10-year return period, I'm having some 2,200. And for 50-year, I'm having some 6,000. So this is just some random values which I'm giving. So when you are doing the actual analysis, you try to give the, then you have the boundary conditions as we were discussing, upstream and downstream. So I'll take the normal depth. So here I'm giving it as 0.001 for upstream and 0.025 for the downstream condition, and say OK. And now I'll save this flow data. It is asking me to save flow_1. Okay, so now I have saved the flow data. You can close this window. Now what I'll do is I'll go to run. And what we are right now we are doing the study flow analysis. So under the study flow, you can select subcritical floodplain mapping, short ID. You can give any ID 22, and you have all the river and flows. So now I'll say compute. The moment you say compute, with respect to the input, whatever you have given, it will start computing. Now it is completed, and you'll close this. And now you'll go to GIS and RAS Mapper. So once you open the GIS and RAS Mapper, already we have conducted the analysis. The results have come. So you can see this. With respect to geometry, we have already seen. So here, depth for the 2-year, you can see how it is going to spread. Then velocity, and similarly the depth also, if you would like to see with respect to the channel configuration. So, and you can see here what are the depth, minimum and maximum depth. Okay, and encroachments and all other things also you can visualize. Okay, so since we gave mostly the arbitrary values, so it is taking away from the river reach, and it is showing wherever the elevation is lesser. So here you are having more depth. Okay, but if you give the actual values, you can simulate it better. And also you have an option to, animate this. And with respect to the duration, how the flow rates are going to vary. So that can also be simulated. So that was the end of this demonstration session. And I would like to thank the entire organizing committee for this opportunity. And thank you once again. If you have any doubts, please ask. Hello?
Yes, sir.
Yeah. So if you have any doubts, you can please ask.
Yes, yes. Participants have any doubts, you can ask to sir. I think sir, no one ask any queries.
Okay.
Yeah, sir. So now we will move to the end of the session two of third day of ISE 2025. Once again, I thank to Chandan sir, Dr. Chandan sir, for accepting and giving the valuable lecture. I think whatever teacher sir given the lecture today, it is very useful. Recent days, in India, many of the places flood is happened. So in future, we may expect few more states also. So this lectures will help to solve this future problem and also in the current problem also in India. Thank you, sir, once again for giving valuable lectures and spending time to us with us. Thank you, sir.
I would like to thank the coordinators, our Dr. Vishal Singh and Dr. Sai Priya. So thank you so much for giving me this opportunity. Thank you very much.
Yes. I will share the feedback link in the chat box. All the participants kindly give your feedback. Thank you, sir. Thank you.
Okay, thank you. Thank you, one and all.
Yes, sir. Yes, sir.
The participants, anyone want to ask anything to sir? You
Sir.
you drop a message in chat box.
Nakiran sir.
Yes, sir.
Yes, sir. Yes, sir. Already concluded.
Okay, sir. Okay, sir. Thank you, sir. Thank you, sir.
సరేనమ్మా